Hi, my name is Qianfan, and this is a presentation of the paper Practical Algorithms and Experimentally Validated Incentives for Equilibrium-Based Fair Division. This is a joint work with Eric, Ruiquan, Abraham, Aviad. The slides are made by Aviad, and Ruiquan and I are going to present our paper. In this paper, we focus the course allocation problem, which is the problem of allocating course states among students in places such as universities. Though in computer science, many classes are basically uncapped since they are lecture-based. Yet, most discussion, project, or sports classes have enrollment caps. And in some scenarios, such as MBA program or law schools, the allocation could even be career trajectory changing for students. So, given that the seats are limited, how should one allocate them to students? And first of all, how should one even model this question? The input of the problem is straightforward. Each student may have a private preference over possible bundles of courses, namely schedules. Each course will have a capacity, which is the maximum number of students can be allocated to it. And courses are indivisible for sure. Having this input, how should we allocate this limited seats? There are some existing methods for doing this, such as zero dictatorship, op auction, or HBS mechanism that used by Harvard Business School. All of them suffer from some drawbacks. Some are not fair, some could be manipulated, etc. On the other hand, here is an equilibrium concept called CEEI, namely competitive equilibrium from equal incomes, which could produce allocations satisfying many super nice properties. Basically, each student is given the same amount of fake money, and we will try to find prices for each course and corresponding allocation such that the market clears and every student gets her favorite bundle she could afford. However, the bad news is the equilibrium doesn't always exist. Nevertheless, Budish developed A-CEEI, an approximate version of CEI in his fascinating work back in 2011. In A-CEI, the market only need to be approximately paired up to a constant alpha, and every student would receive a different budget within the range from 1 to 1 plus beta. In this way, we can prove that A-CEI always exists with respect to reasonable parameters. Namely, alpha is in the order of number of courses, and beta can be made arbitrarily small. The good news is that many nice properties from CEI basically remain. It satisfies a property called strategy proof in the large, which means it cannot be manipulated in a large enough market. It also approximately Pareto optimal, and is envy-free up to one course. However, to make it work in practice, we have one thing left. That is, we'll need an efficient algorithm to find the equilibrium. It turns out that A-CEI is a hard problem, in theory at least. As you can see, Aviad has many great papers on the hardness of A-CEI during his PhD. Meanwhile, in practice, there is a heuristic algorithm based on work from Othman, Zhang, and Budish in 2010. The algorithm is commercialized by Cognos and used in several MBA and law programs. The algorithm is not super fast, however. It may take a few days of heavy computation for a single run. Now I'm going to introduce our contributions in this work. First of all, we developed a much faster heuristic algorithm, and it is extensively tested on empirical datasets provided by Cognos. This is a comparison of running time and clearing error between different versions of our algorithm and the previous heuristic algorithm used by Cognos, namely benchmark. There are about 500 students and 125 classes in this specific instance, which doesn't sound terrible, but it is considered to be huge for their previous algorithm. As you can see from the blue line, even after 4 hours, it reduces the clearing error very slowly, while the green line, which represents the faster version of our algorithm, found a zero clearing error equilibrium within 1 minute. That is to say, we developed a much faster heuristic algorithm, and the algorithm is not only faster, but it also gives a better allocation. The benefit could be now schools can have more time to interact with the algorithm. More importantly, this enables us to analyze incentives for A-CEEI mechanism on real instances. This is important even we know that A-CEEI is strategy-proof in the large, since you will need large here to be very large for the theorem to hold. Exponential in the number of courses is not enough. Actually, for the theory result to hold, one must have number of students in the order of doubly exponential of number of courses. So basically, the theorem might not be applicable in many real scenarios. Yet in practice, we didn't expect students would be able to manipulate A-CEEI. Surprisingly, however, we did discover some interesting yet simple manipulations in real instances. Actually, it's not us, but an algorithm that discovered these manipulations. We have designed an algorithm to find possible manipulations and test them. We got some very interesting observations from them, and having these observations, we went back and made the mechanism more strategy-proof. During the process, we have discovered a new notion of fairness. We name it contested envy-freeness. As you might know, envy-freeness is one of the gold standard for fairness. The definition is simple. An allocation is envy-free if no agent prefers another agent's allocation. It is a very strong notion, which makes it often infeasible, and there are a lot of work based on relaxations of envy-freeness. However, is envy-free always truly fair? Let's consider the following scenario. Say my cousin Eric drives an old Honda and Mohammed, Aviad's neighbor, drives a Porsche. Would Eric want to switch his Honda with Mohammed's Porsche? The answer is no, because Eric's keys are in the Honda. Eric's keys are cute, but only Eric wants them in his car. They are uncontested. However, if we restrict to contested goods, namely cars, Eric would envy Mohammed's Porsche. So, I'm going to briefly introduce the formal definition of contested envy-freeness. First, we should define what makes a good uncontested. Intuitively speaking, a good is uncontested if it is under-demanded. Specifically in the setting of A-CEEI, since there is a price, we call good uncontested whenever its price is zero. Yet, this is only a definition for A-CEEI, and it would be interesting to find a better formal definition in a more general way. Now, our intuition for contested enviness is that one should contested envy other if their allocation is better when restricted to only contested goods. In the formal definition, we instead say that agent I will contest envy some other agent J if I would prefer J's allocation plus those uncontested goods chosen freely. Recall the previous example between Eric and Mohammed, where the Porsche and the Honda are contested, and Eric's keys are of course uncontested since keys are prices. Note that Eric doesn't envy Mohammed since he values his keys much more than a Porsche. However, Eric does contest envy Mohammed since his keys are uncontested and he should be always having them when comparing to others. And finally, we say an A-CEEI allocation together with prices satisfy contested envy-free if no agent contested envies any other agent.
Hi, I'm Ruiquan. Next, I will talk about our new algorithm. We consider the traditional tautology algorithm, which is a try-and-error process to compute market equilibrium prices. More specifically, we start with some initial price. In each iteration, we compute the student's demand. If a course J is oversubscribed, we increase its price. Otherwise, if it's undersubscribed and has non-zero price, we decrease its price. For example, Alice and Bob are the students who want to take CS 101, and they both have budget 1. If the initial price is 0, the course is oversubscribed and we need to keep increasing its price until the price becomes strictly greater than 1. At this time, both an Alice and Bob cannot afford the course and CS101 becomes undersubscribed. So we need to decrease its price. Afterwards, we will increase and decrease the price alternately, and the algorithm cannot stop. So now the question is, when should we stop the algorithm? Recall in the definition of A-CEEI, we are allowed to perturb the budget. For example, we can assign Alice a budget of 1.05 and Bob a budget of 1.1. Now, when the price is 1.07, we found an equilibrium. So now the question becomes, how should we choose budget perturbations? The original existing proof of Budish chooses randomly infinitely small budget perturbations. However, the proof highly relies on the fixed point theorem, which is hard to implement efficiently. Because of this, the previous algorithms used in practice consider larger random perturbations. Even though this choice still requires a lot of computation to find a reasonably small market clearing error. In this paper, we provide a new idea that we choose the optimal budget perturbation so that the clearing error is minimized. And with this idea, we can also use a smaller perturbation. More specifically, when we compute the student's demand given the current price, we consider each student's all possible demands at all possible perturbed budgets. Using all these demands, we can solve an integer linear program to find out the optimal perturbation that minimizes the clearing error. Then we shall use the demands under this optimal perturbation to update the prices. We note that though this step 1b solves an NP-hard problem in theory, modern set solvers can implement this step very efficiently. And it turns out that our algorithm can help find zero clearing errors and reduce the clearing error significantly faster than the benchmark, which is the previous commercial state of the art using a single cost price adjustment trick on the Tautman algorithm. You can see from the red line, which is only a simple implementation of our algorithm, proceeds much faster than the benchmark. With a few more tricks mentioned in our paper, we further improve the running time significantly, for example, from 3 minutes to 1 minute on this instance. Besides the speed, we have many other concerns in the cost allocation problem. For example, it is tempting to ask, is this algorithm strategy proof? Unfortunately, the answer is no. In this paper, we have shown very simple and robust manipulations by which students can improve their allocations with a very small risk. So, is this algorithm strategy proofish? Previously, A-CEEI with random budget perturbations is shown to be strategy proof in the large. Recall the definition of strategy proof in the large. As the number of IID agents goes to infinity, the mechanism becomes incentive compatible. This fact is established via a notion called envy-free but for type breaking, abbreviated as EFTB. Well, given a random order, you can never envy a student with a lower order. In A-CEEI, the random order can be the random budget perturbation, and the students with higher budgets can never envy students with lower budgets. So A-CEEI can be EFTB with a random budget perturbation. Further, every EFTB mechanism is shown to be strategy proof, assuming we have a full support type distribution. Though here some issues may arise because our algorithm uses optimal budget perturbation instead of random perturbations. We have a very easy fix. As we just saw, every EFTB mechanism is strategy proof in the large. Given a random ordering, we can simply enforce the EFTB constraints in the integer linear program when solving optimal perturbations, so that we can guarantee strategy proof in the large for our algorithm in theory. However, the market in practice cannot be as large as a theory of structure-proofness in the large needs. We still need to look into the structure-proofness on real-world instances. To do this, we developed an approach to find deviations. Well, we start from the true base of the students and look for profitable deviations with greedy hill climbing algorithm by repeatedly running our fast algorithm of finding a cost allocation. For experiments, we consider two different models of the student's uncertainty in running our algorithm. First, we consider resampled randomness, where we resample students' ranking for EFTB constraints in different runs of the algorithm. Second, we consider resampled population, where we redraw students' population from empirical distributions in different runs of our algorithm. The experiment suggests a more strategy-proof algorithm in which we incorporate our new notion of contested n-way-free but for tie-breaking into our algorithm. Here we present our empirical statistics. You can see that our final algorithm enforcing contested EFTB is the most strategy-proof one, and compared to that enforcing no classic EFTB and the Harvard Business School mechanism. It almost eliminates all the profitable deviations found by our deviation finding approach on other three mechanisms. However, due to some limitations of our experiments, we cannot say that our final algorithm is strategy-proof in practice. We only finished experiments on 3 schools, and only one of them has significant manipulations with no classic EFTB. We only have small sample sizes in the experiments, and our greedy deviation finding approach cannot perfectly simulate all the strategic students. Finally, conclusions. In this paper, we present a faster algorithm computing A-CEEI. Due to Kamal-Jain's famous formulation, if your laptop cannot find it, neither can the market. We significantly expand the market equilibrium that your laptop can find. However, it is hard to say PPAD is easy in practice. If it's really easy, we could have solved it faster with arbitrarily small perturbations. And another strange thing is, as A-CEEI have no zero clearing error solution in theory, the problem our empirical algorithm solves isn't even in PPAD. So we are very biased with what this empirical result suggests for PPAD in practice. In addition, our fast algorithm is already making a difference in production. Because of its fast speed, we give the first analysis of A-CEEI incentives on real instances. Though we have a theory of strategy proof in the large, it is still very necessary because we cannot expect the real market to be as large as the theory needs. During the analysis, we designed algorithms that discovered some surprising manipulations. Afterwards, we went back and made the algorithm more strategy proof. During the process, we also discovered a new notion of fairness, contested n-way free, which can be more incentive compatible than n-way free on A-CEEI. That's all. Thank you.